11. Heat exchangers. Welcome to our session on heat exchangers, a crucial component in almost every thermal system you'll encounter. Whether it's in power plants, air conditioners, car engines, or even your home refrigerator, heat exchangers make thermal systems efficient by transferring heat from one fluid to another without mixing them. Think of it like passing a hot potato through a wall. The heat travels, but the potato doesn't. Throughout this chapter, we'll explore the main types, working principles, and performance analysis of heat exchangers. By the end, you'll not only know the types, but also understand why design choices matter for efficiency and performance. Get ready to see the hidden champions of energy systems in action. Simple, smart, and indispensable.
1. Learning outcome. Before we dive deeper, it's always helpful to know what you'll walk away with after this session. Good learning outcomes should be practical, clear, and linked to skills you can apply. Here, we focus on real-world heat exchanger knowledge, not just theory. You'll learn to classify different types of heat exchangers, calculate the overall heat transfer coefficient considering fouling, and apply energy analysis techniques. We'll cover two essential calculation methods, LMTD for when temperatures are known, and effectiveness NTU for when they are not. Finally, you'll know how to select the right heat exchanger in practice, not just on paper. By keeping these goals simple and application-focused, we make sure every part of this session serves a purpose, giving you tools you can actually use.
2. Introduction to heat exchangers. Let's start with the big picture. Why do we even need heat exchangers? Their core job is simple: transfer heat between two fluids without letting them mix. Like a chef flipping a pancake without breaking it. You transfer heat, but keep things separate. They're everywhere, from HVAC systems keeping your room cool, to power plants making electricity, to chemical industries running complex processes, and even your fridge. Heat exchangers are invisible heroes in thermal systems. The way they work involves convection happening on both fluid sides and conduction through the barrier separating them. All these steps create resistance to heat flow, but we simplify everything into one term: overall heat transfer coefficient, or U. This U value tells us how good the system is at transferring heat. By understanding these basics, you'll see heat exchangers not as mystery boxes, but as logical, efficient tools we can design and improve.
3.1. Types of heat exchangers. Let's make sense of how fluid flow affects heat exchanger performance. Flow configuration is a big deal. It controls how effectively heat moves between fluids. In a parallel flow exchanger, both hot and cold fluids enter at the same point and travel together in the same direction. Sounds simple, but the temperature difference drops fast, making it less efficient. Counterflow is the opposite. Fluids enter from opposite ends and move against each other. This keeps the temperature difference higher for longer, meaning more heat transfer and better efficiency. Then there's crossflow, where fluids move perpendicular to each other, like in car radiators or air-cooled systems. Each type has its own strengths, but the rule is simple. Counterflow is most efficient, parallel is simplest, and crossflow is very practical when space and airflow matter. By knowing the flow pattern, you can predict performance before even touching the calculator.
3.2. Types of heat exchangers. Construction matters. Let's look at how heat exchangers are physically built, because this affects their use and efficiency. First is the double pipe heat exchanger. It's as simple as it sounds: one pipe inside another. It's good for basic, low heat transfer tasks, but don't expect high performance from it. Next, we have compact heat exchangers. These are designed to pack a lot of surface area into a small space.
Think of car radiators or your lungs. Lots of area for heat exchange without taking up much room. When you need efficient heat transfer in a tight space, this is the go-to option. Finally, there's the workhorse of industries, the shell and tube exchanger. Picture lots of tubes bundled inside a shell with baffles that guide the flow for better heat transfer. This is the most common type you'll see in factories, refineries, and power plants because it balances efficiency, flexibility, and easy maintenance. Keep it simple: double pipe for low needs, compact for space saving, and shell and tube when you need industrial strength.
3.3 Types of heat exchangers. Now, let's go a little deeper into construction. Beyond pipes and shells, we have more advanced designs that solve specific problems. First, the plate heat exchanger. Imagine stacking plates like a deck of cards. Each plate channels hot and cold fluids in alternate layers. This maximizes surface area and creates a compact, highly effective heat exchanger. Great when you need high performance but have limited space. Then there's the regenerative heat exchanger. Instead of both fluids flowing at the same time, they take turns. Hot fluid heats up a solid matrix, and then cold fluid absorbs that stored heat. It's like preheating your oven before cooking. This method is especially useful in applications like Stirling engines or recovering waste heat. The takeaway here? Plate types are for compact, high-efficiency tasks. Regenerative types are for systems where you can store and release heat smartly.
4. Overall heat transfer coefficient, U. Let's simplify what controls the performance of a heat exchanger. Heat doesn't just magically move from hot to cold. It moves through two key mechanisms, convection and conduction. To capture this, we use a thermal resistance equation. Think of it like adding up roadblocks, resistance from the inside fluid, from the wall, and from the outside fluid. All these slow down heat transfer, and the overall heat transfer coefficient, U, tells us how good the whole system is at moving heat. But there's a hidden villain: fouling. Over time, dirt and scale build up on surfaces, like cholesterol in arteries, making heat transfer less efficient. We measure this using a fouling factor, RF. Higher fouling means worse performance, which is why industries monitor and clean heat exchangers regularly. The key takeaway? U reflects the combined effects of flow, materials, and maintenance. Keep U high, keep efficiency high.
5. Log mean temperature difference, LMTD method. Let's talk about one of the simplest yet most powerful tools in heat exchanger analysis, LMTD. Whenever you know both inlet and outlet temperatures of the fluids, you use LMTD to calculate the driving force for heat transfer. The formula looks complicated, but the idea is simple. The temperature difference changes along the length of the exchanger, so you take an average, but not just any average, a log mean average, because temperature change is exponential, not linear. If your heat exchanger has multiple passes or crossflow patterns, things get a bit messy, and that's where the correction factor, F, comes in. It adjusts the LMTD value to keep your calculations accurate. Bottom line, LMTD is straightforward when you know all temperatures. Just don't forget the F factor for complex flow paths.
6. Effectiveness NTU method. Now let's deal with situations when we don't know the outlet temperatures, a very common problem in design. That's where the effectiveness NTU method comes in handy. Effectiveness simply tells us how much heat transfer we're getting compared to the maximum possible. Think of it like a scorecard. 100% would mean we're transferring the maximum heat possible. To find this maximum, we use the minimum heat capacity rate, Cmin, which is limited by the fluid with the lowest ability to carry heat. The number of transfer units, or NTU,
connects the heat exchanger size to its performance. More area, better U, or smaller C-min. Your NTU increases, meaning more capacity to transfer heat. So when you don't have outlet temperatures, this method helps you predict performance just by knowing basic design data. Bigger NTU equals a stronger heat exchanger. Simple and practical.
7. Heat exchangers selection criteria. Let's finish with what really matters in practice. How do you choose the right heat exchanger? Your goal is to get the performance you need, at the lowest cost, with minimal headaches later on. First is heat transfer rate. Always ask, will this unit deliver enough heating or cooling? Next is cost. Think not only about the purchase price, but also maintenance and energy use. Pressure drop is another hidden cost. High resistance increases pumping power and hurts efficiency. Size and weight matter too, especially in cars or planes where space is a premium. And don't forget materials. Stainless steel and titanium fight corrosion, while aluminum wins when weight matters. A smart choice balances these factors, not just picking the biggest or cheapest unit, but the one that performs efficiently, reliably, and affordably in your application.
8. Engineering applications. Let's end with why heat exchangers matter in the real world. These are not just textbook concepts, they solve critical problems across industries. In power plants, they help condense steam back into water to complete the cycle. In cars, radiators prevent engines from overheating. In refrigeration systems, they cool down or remove heat using evaporators and condensers. Electronics need them too. Heat sinks keep chips cool and prevent damage. Even in food processing, heat exchangers help with pasteurization and sterilization, making products safer to eat. Heat exchangers are everywhere, keeping systems safe, efficient, and functional. That's what makes them essential in engineering practice.
9. Summary. Let's wrap it up with a quick recap, keeping it simple and clear. Heat exchangers transfer heat between fluids while keeping them separate, playing a huge role in many industries. You've learned about the main types, from basic double pipe to industrial shell and tube and high-efficiency plate exchangers. When temperatures are known, use LMTD. It's direct and practical. When temperatures are unknown, the effectiveness NTU method guides you based on system limitations. Finally, your selection always comes back to fundamentals: heat transfer rate, cost, pressure drop, materials, and size. Focus on these, and you'll always make the right design choice.